Hey guys. Okay, so we're going to continue on with chapter 2. It's a little bit longer of our chapters this semester. You'll see in the syllabus we have it planned out for 3 days of lecture, releases, or whatever you want to call it. Okay, and so the first thing we're going to do is we're going to talk about the periodic chart. Okay, and this is my favorite periodic chart. I bet you don't have a favorite, yeah, it's just so colorful. The colors all mean something, and it just has so much information on it. This is going to be posted on the Blackboard page for you so that you can download it and refer to it and use it, so forth and so on. The story of how the periodic chart developed and was invented is a fantastic story. We get into it a little bit later on, but not in too much depth. Don't have a lot of time, but it's kind of a remarkable story. A lot of atoms were predicted before they were actually discovered. There must be something in that place with that type of electron and proton type of configuration, and lo and behold, they end up finding it. And so we'll go through in a real organized fashion and stuff, but in general, you have the main group elements, and the main group elements are these two columns here, okay, and then these 6 columns here, okay. So main group includes these and these, and then these are the transition metals, okay. What else? The columns are called groups. The horizontal lines are called periods. The first group, first column, are the alkali metals, and the second column is the alkali earth metals. And then you have another sort of, oh well, I should mention these guys. These are the noble gases, and they are the only type of elements that are solitary creatures. The atoms of these elements hang out by themselves. They don't bond with nothing. We'll learn a little bit later on that their configuration, their particular configuration of protons and electrons is just perfect. They don't need anybody else. I'm sure there's some horrible, cheesy dating analogy I could make, but I am going to resist the temptation. Yeah, so those are the noble gases. And then another important delineation, if you can see right here, there's, what is that? Is that salmon? This color? I don't know. Or maybe it's pink or something. Whatever this color is here. That's sort of a border, okay? And everything to the right of that are non-metals, and everything to the left of that are metals. And then things that actually border the line, the salmon or pink or whatever the heck that color is, those elements are called metalloids, okay? And so the metals have particular characteristics. You know, there's always some variations, but some generalizations that you can draw about metals. They're shiny, they conduct heat, they conduct electricity, shiny, electricity. They're malleable, you can bend them, so forth and so on. The non-metals tend to be solids or gases or liquids. The metals tend to be all solids except for mercury, the only liquid non-metal. Or I'm sorry, the only liquid metal. Okay. These tend to be insulators rather than conductors. Blah, 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 blah. And the metalloids have a little bit of both characteristics. Okay, they're right in between. Okay, so let's put some text to all of that mumbo jumbo. Okay, so wanted to tell you guys that when I'm up here all the time, I keep on thinking my handwriting is getting way better, and I'm always like, oh, right on, we're doing way better. And then I look at the video and I'm like, no, it's not at all. I'm trying. I'm desperately trying, guys. Okay. How organized. Okay. The simplest organization is the atomic number, 1 to 111. Okay? All right. There are many aspects of, which I introduced to you a second ago, many aspects of organization. Many different ways you can organize them. Okay. There is groups versus periods. Okay. Just colored here. The columns up and down are groups. Okay. Oh yeah, and an important thing that I didn't talk about is that in general, elements in the same group have similar reactivities, similar physical properties, so forth and so on. Okay. Whereas when you start moving horizontally across a period, it changes very quickly. Okay. In the original Star Trek, apparently there was something that, well, rather than carbon-based life forms, there's silicon-based life forms. And clearly the people who invented this idea, I don't really, I didn't really know the show, but the people who made it clearly knew something about chemistry because silicon is right under carbon and it bonds similarly and has similar physical properties, so forth and so on. I mean, it definitely differs, it's a different element, but there are certainly similarities. Okay, sorry. Okay, so elements in the same group have similar properties. Okay. The first two columns or I'm sorry, first two groups. Let's call that, and then I'll put here columns, so you remember. Okay. Plus the last six. Those are the main group elements. Okay. And then the columns in between groups are transition metals. Okay. All right, now the groups can be numbered two different ways, and if maybe you've downloaded your gorgeous periodic chart, as I call it, you'll see that they have different numbering systems on the top. Let's see. I don't want to get too close to you guys. Okay. Oh no, that's okay. Okay, so you can see up here that the main groups are numbered with Roman numerals and the letter A. So 1A, 2A, skip all the way over here to 3A, 4A, 5A, 6A, 7A, 8A. Okay, and then the transition metal, sticking with it stays with the Roman numerals, except it switches to B. So, there's 1A, 2A, then 3B, 4B, 5B, 6B, 7B. Those are combined together, so forth and so on. things get confusing with the transition metals, okay? Alternatively, and not all period, you might have a different periodic chart and it only has one of these numbering systems, or it just numbers them 1 through 18, okay? So 1, 2, 3, 4, 5, 6, 7, 18, okay? All right. So groups, which are the columns, I don't know if I need to keep reminding you, can be numbered in a couple of different ways. Okay. They can be numbered 1 through 18, okay? Or they're sort of the main group. And I think this second way is the more common way people talk about it. Group 3A elements, group 4A elements, so forth and so on, rather than just giving a simple number. Okay, so main group is 1A, oh, this is a weird way I've written this in my notes. Okay, well, maybe it's not. We'll see how it works. Okay, 1A and 2A, okay. Then the transition metals, okay, and that is 3, and actually these should be Roman. See, the thing is sometimes they don't use Roman in other periodic charts. I think I was looking at one that didn't, but let's stick with the Roman since that's the chart you have in front of you. 3B to 8B. So sorry. 8B. Okay. And then the rest of the main groups. Okay. And that's going to be 3. Come on, you need Roman numerals. Can you go? 3A to 8A. Okay. All right. And then some groups, as I mentioned earlier, have names for that group. Okay. One A is the alkali metals. Okay. 2A is the alkali earth metals. What else do I include? 7A is the halogens. And then I also mentioned the noble gases in 8A. Okay. Light. Yes. Sorry. The rows are called periods. Okay. And so period 1, if you look at your chart right now, it's just 2 elements. Hydrogen and helium. Okay. And it may seem funky that, why did they make this big dip in the periodic chart? There's very good reasons for that in terms of their electron configuration being similar. Anyway, we'll get to that a little bit later on. Okay, so still looking at the different ways that the chart is organized. All right. There's metals versus nonmetals. Okay. There is a squiggly, how do I spell squiggly? S-Q-U-G-G-L-E-Y. Squiggly line from boron to antimony. Boron, which is B. Okay. Okay, and so there's that squiggly line, and in ours it's that salmon colored, just the elements themselves have a particular color to them. In some periodic charts you actually have a sort of a bold line that wiggles down the chart at that location. Squiggly line, okay. Elements to the left line are metals. Okay. And by the way, it should make some sense to you, even if you've never seen the periodic chart before. You have things like lead and what else is everybody familiar with? Copper. Those, we think of those in everyday life as metals, so that makes some sense. And elements to the right of the squiggly line are nonmetals. Okay. Border elements okay. Touching the line those are metalloids. Okay. And they, right yet, they behave sort of in between metal behavior and non-metal behavior. Okay. Semiconductors. So, we said that the metals are conductors, the nonmetals are insulators, so they don't conduct. Well, the things on there are semiconductors, and lo and behold, those are the elements you find in semiconductors. I think silicon is common in semiconductors. In electronics is what I'm talking about. Okay. Still espousing on stuff I don't really know much about. Okay. So some important trends to appreciate that I discussed earlier. Okay. Metals tend to be solid, lustrous, that means shiny, conduct heat, conduct electricity, and malleable. Okay, so you can bend them. Okay, we're back at it here. All right, so metals are malleable. The non-metals tend to be solids and gases. Okay. And one liquid, that is bromine. And they tend to be insulators. And by that we mean heat and electricity doesn't pass well through them. Okay. All right. So let's take a little look now at compounds. Okay. We've already discussed a little bit that compounds can be broken up into two classes. There's molecules, okay, where atoms are in a group, they stay with that group, they go everywhere with that group, so forth and so on. And then there are ionic compounds, or salts. And ionic compounds and salts are made up of cations and anions. There are certain types of elements, i.e. metals, that become cations well, okay? And they become cations because they don't hold on to their electrons terribly well. Okay, they give up electrons fairly easy. And they are always slow down. The ionic compounds are typically made up of metals and nonmetals, okay? And the metals don't hold on to their electrons very well. They give up electrons, and if they give up an electron, that means they have more protons in their core than they do on the outside, okay? Than electrons on the outside, and so they become a cation. They become a positively charged ion, all right? The non-metals, on this side of the periodic chart, the non-metals actually, they're good at stealing electrons. So, and if a non-metal steals an electron, now it has more electrons in its outside area than it does protons in the core. Okay? Remember, a neutral atom has the same number of protons in the core as electrons out here. Okay? So if a non-metal takes an additional electron, stealing it from some poor helpless metal, it will have an excess of electrons compared to the protons in the core, and it becomes an anion. okay? And so not inorganic, scratch that. Ionic compounds and salts are made up typically of metal cations and non-metal anions, okay? And then molecular compounds, the ones where they travel together everywhere, they are made up of all different types of non-metals, okay? There's no metals involved in molecular compounds for the most part, okay? All right, so I'm going to start with molecular compounds. Okay, in general. Okay. First, remember the word compound implies two or more elements. Okay. Also, remember, there are two types of compounds. Okay. Ionic versus molecular. Okay. All right. But molecular compounds or otherwise known as molecules, are typically small, okay, usually nonmetals. Sometimes you might get some metalloids involved there. Okay. Permanently attached. Okay. And I have in my notes here to mention to you that through a chemical reaction they can be detached. Okay. And then you have ionic compounds. Okay. Oppositely charged ions. Okay. That associate in a large group, and by large I mean billions and trillions and zillions. I mean an individual grain of table salt. How many sodiums is that? Let me do some quick, just thinking about that. It's probably like, I would say, probably like 10 to the 20 sodiums. Okay, whatever that number is. That 1 grain of not even Hawaiian salt, thin salt. Okay. Oppositely charged ions that associate in large, what do I want to call it? Large group through electrostatic attraction. Okay. Electrostatic, it's really just, there's more sort of detailed definitions, but you can just think of that as the idea that I've mentioned a few times, I believe, that oppositely charged things are attracted to each other, like charges repel each other. Okay. And so it can be looked upon as it's two different strategies of bonding. Okay. All right. So moving on, I did kind of both ionic, an overview of ionic and molecular there. But moving on now with molecules. Okay, so there are diatomic molecules. Okay, that's just two atoms together. Okay. And within that class, diatomic molecules, there are some elements that actually exist in their natural form as diatomic molecules. Oxygen, the halogens, nitrogen, hydrogen, they exist. When you find oxygen out in the air or out in the world, or you're breathing it into your lungs right now, it is the diatomic form of oxygen. Okay. But you can also have compounds that are diatomic, so HCl, HBr, things like that. Carbon monoxide. Okay, so few elements exist in in pure form as diatomic molecules. Okay. Oh, that's meant to be a whole one. Okay. Small. I'll do the pure element diatomics up here. Basically, just the ones I just mentioned. So hydrogen, oxygen, nitrogen, and all the halogens. Okay. Fluorine, chlorine, bromine, iodide. Okay, or iodine. All right, I have a mention in here that kind of almost FYI, oxygen can also exist as O3. Okay. And that is ozone. Okay. And that has, it's one of the many things that I love about chemistry. You make a slight change on a molecule and it has just extraordinary differences. Ozone is very reactive. It can cause pulmonary edema. We sometimes use it as a laboratory chemical to do changes, and so you need to be sure to do it in a hood so that you don't end up breathing it. It smells, if you use it, you end up breathing a little bit. No problem so far. Still good. It smells a little bit like fresh laundry. It's actually a really pleasant smell. But you make one small, you add it, and that's totally different from oxygen that we breathe in our lungs and stuff. Carbon dioxide, totally innocuous. This room is full of it. Carbon monoxide is a poison that will kill you very quickly. Okay, so now we're going to talk about empirical formulas and contrast them with molecular formulas. Empirical formula, it's just the ratio of atoms, okay, in a compound. All right, sodium chloride, 1 sodium, 1 chloride. Blanking right now. Shucks. I don't know. Calcium chloride, I think it's the same. Sometimes I want to have different examples than what I put on the board, but calcium chloride, that is 1 calcium, 2 chlorines. Okay. So the empirical formula is the ratio, but it's the simplest whole number ratio. Okay, so perhaps your ratio of compounds that's the simplest whole number ratio of atoms in your compound. In a molecule, okay, you could have 5 carbons and 10 hydrogens. Okay, that's that's something called pentene. All right, so you can have 5 carbons, 10 hydrogens, and so the molecular formula needs to describe what's actually in the compound, what's floating around. They're all, they go every place together, like I said. And so the molecular formula of that would be C5H10. Okay, but that's not the empirical formula, because the empirical formula is the simplest whole number. So the empirical formula of pentene is 2 to 1. Okay, or I'm sorry, C1H2. Okay, so that's the difference between the two. It's really no more complicated than that. All right. Empirical formula versus molecular. Okay. Empirical, let's just say F, that is the simplest whole number ratio. Okay. Whole number meaning that it can't be, 1.5 or something like that. Whole number ratio of the elements in the compound. Okay. All right, so some examples. Okay. So I'm going to start that up there. So what I'm going to start with is the compound butane. It's actually what's in cigarette lighters, butane lighters. Okay, so the actual molecule itself looks like this. There's carbons, and they're bonded, and we haven't even broached the subject of what does a bond mean yet. Don't worry about that. They're attached. Okay. And then you've got hydrogens all around. Okay. So you have 4 carbons and you have 10 hydrogens. Okay. Simplest ratio is 5 to 2. Okay? Therefore, international symbol for therefore. Empirical formula is C2H5. Okay. The molecular formula okay. The actual number of atoms of each element in a molecule. Okay. Therefore, the molecular formula for the above is, what the heck is it? It's C4H10. Okay. So, some things that we're going to see in a second. Ionic compounds only have an empirical formula, right? Because you remember there's no particular one cation that's associated with one particular anion, okay? So the formula is simply the simplest ratio, okay? Molecules have both, and sometimes the molecular formula equals the empirical formula, okay? If you have ethane, it is C2H. Oh no, that's not a good example. I'll have one here in a little bit where they are the same. Okay, the ones that hang around do so in the simplest whole number ratio. So the molecular formula equals the empirical formula. Okay. Another one. All compounds have empirical formulas. Okay. Only molecules have molecular formulas. Okay. Oh yeah, and this is an important point. The molecular formula, MF, is always an integer multiple of the empirical. The empirical formula, EF. Okay. So in the above example, you had C2H5. Okay. Well, and so that's the EF. Okay. Multiply that due by 2, and then you have C4H10. Okay. And that is the MF. Integer multiple. Okay. All right. Move right along. And yeah, I'll put this in your notes so it's there. Sometimes the EF is the same as the MF. Okay. Let me show you an example of that. Okay, you can have this compound. Okay. That is actually isopropyl alcohol. I'll just put as a side note. Okay. This is the structural formula. Shows what's bonded to what. You don't know that information in a molecular formula. Okay. Sometimes, often, it's just called the structure. Okay. And so the MF of that compound, of isopropyl alcohol, rubbing alcohol, is C3H8. Oh, okay. That is the simplest whole number ratio, so it's also the EF. No, it's not how you spell empirical. EF. Okay. All right. Okay. Ionic compounds only have empirical formulas. I don't know why I keep on wanting to spell empirical with an I. Sodium chloride, that's an ionic compound. By the way, we're going to learn a little bit the way you can recognize an ionic compound. Well, I've already mentioned it, is you have one of the metals, one of the things on the left side of the squiggly line, and you have a non-metal, one of the things on the right hand. If you're looking at a compound, you're wondering, is that a molecular compound? It'll be all non-metals, things to the right of the squiggly line. Okay, another ionic compound. Potassium permanganate. Okay, I have like a little sneak preview here. I believe it's because I keep this fairly consistent with the textbook that we're using, and so they have this in here, so I will include it. Not very long. Just a sneak preview on bonds, on molecular bonds. So there's different types of bonding. Molecular bonds, bonds of molecules where they're going everywhere together and stuff. These lines that I drew, those are a shared pair of electrons. It's two electrons that is being shared by both the carbon and the hydrogen. Okay? For reasons that we'll get to in a little bit, carbon walking around in the world doesn't have quite as many electrons as it would like to have. Okay, it would like to have, well, well, we'd like to have more electrons, same with hydrogen, so they come together and say, hey, I've got this one, you've got that one, why don't we share those, and we'll add that to our total. Okay? All right, so, molecular bonds. Okay, let's call this a sneak preview. Okay, bonding strategy. Okay. Atoms in a molecule share electrons. Okay. In any bond, two atoms share one of their electrons. Okay. With the other, or with each other. Okay, and is typically indicated by a line when you're, writing molecular bonds on a board. Okay, they're anything but a line in the real world, but written on a whiteboard, they're a line. All right. So we need another example. We have our isopropyl alcohol up there. So this means two electrons being shared. Okay. All right. Okay. So let's talk about salts, salt compounds. Okay. As I mentioned, you have nonmetals that don't hold on to their electrons very well, and they, whether they form this way or they don't form this way, they may, but it's a nice way to think of it. Metal's walking along through the world, doesn't hold on to its electrons very well, runs into a nonmetal who is really greedy and likes to take electrons. And so the metal's walking around, it's neutral, got all its electrons. Non-metal's walking around, it's neutral, wants more electrons, steals an electron from me, the metal. I become cationic because I've got more protons than I do electrons because I lost one to theft. All right, and then that non-metal over there now has a negative charge as an anion because it stole an electron from me and has an excess of electrons. And it's outside. And now, and now these metals, they always like the bad boys. No, I'm just kidding, sorry. I avoided the cheesy examples. But now, I'm a cation, that's an anion, and I'm attracted. And I hang out in a compound through electrostatic attraction. Okay. Oops. Okay. Salts, otherwise known as ionic compounds. Okay. Bonding strategies. Atoms are not shared. Somebody stole one from another. Electrons, not shared. Okay. Think of as one atom takes an electron from another. sometimes these things are not that great, but it's just a lot of words. It becomes negative. Okay, anionic. And the other becomes positive. Okay. Some types of elements. Don't hang on to their electrons well. Okay. And these are usually the metals. Okay. Okay, so for instance, put that underlined. You have sodium atom. Okay. Your sodium atom has 11 electrons. Okay, buzz them all around. And it has 11 protons, which I'm expressing here. Earlier I expressed, let's just be consistent. Sorry. Nobody uses P+. Everybody expresses a proton, represents a proton as H+. Okay. Okay, so 11 electrons, 11 protons. Loses an electron. Okay. And now you're looking at now you're looking at, sorry, I get obsessive compulsive about the colors. 10 electrons out here, buzzing around, but nothing's changed in the nucleus. 11 protons, okay? And so this guy becomes positively charged. You have an excess of protons in this species, in this ion, yeah? Okay. Likewise, same thing could happen to chlorine. Oops. Chlorine, okay. You've got 17 protons, you've got 17 electrons, okay. Gains or steals an electron, okay, so that it now becomes 18 electrons buzzing around, but there's still 17 protons in the core, okay, so that this becomes negatively charged, right? And then they're attracted to each other, okay? Then anions, cations. Remember, anions, ants are negative. Cations, cats are positive things. They are. I like cats. Anions and cations come together. Okay. And you get a salt. Okay. Okay. Now, you know, some elements. It turns out that sodium. Yeah. Can I say only? Whenever you're a teacher, you always want to be careful about saying always, only, you don't want to box yourself in, but I can say this here. Sodium only loses 1 electron. You only find sodium plus out in the world. You never find sodium 2 plus out in the world. Okay? Probably Google that and you can probably find that's not true. Don't box yourself in. But 99.999% of the time at least, sodium only exists as N+. Calcium out in the world only exists as 2+. It loses 2 electrons, actually. Okay? Chlorine and all the halogens only exist as a -1 charge. Okay? And nitrogen, when it's in an ionic compound, exists a -3 charge. Okay? So there's specific charges that different types of elements will choose, and it actually turns out that you can predict these much of the time, not so much with the transition metals, but you can predict these from their position on the periodic chart. Okay? For reasons that we'll get into later, or we'll try to explain later, it's actually not that easy a thing to explain. Let me back up. Sorry, let me back up. You know that an atom on the periodic chart, let me get a periodic chart while I'm talking about it. The atoms on the periodic chart, we know that as you go along, the number of protons inside is increasing. Okay, so hydrogen has 1 proton, helium has 2 protons, lithium has 3 protons, okay? And that corresponds to its atomic number. Atomic number 1, atomic number 2, atomic number 3, 4, 5, and so forth and so on, okay? And so the position on the chart actually tells you how many protons any particular atom has. All you have to do is look at the number 27. It's 27 protons, okay? If you're talking about a neutral atom, then the position on the chart also tells you the number of electrons, right? I mean, if it's neutral, it's got to have the same as what's in the core. So that number tells you the number of electrons too. Okay? All right. Now, as it happens, these noble gases have a really good configuration. I mentioned that earlier. That's why they don't bond. Okay? They have sort of the perfect number of electrons. And I'm going to leave that purposefully vague for this chapter. We'll revisit that later. It has to do with their outer shell. They have 8 electrons in their outer shell, and that's the best way to be. Okay, so, but forget about that 8 business, outer shell business. They have a great configuration. And so what atoms do is they gain or they lose electrons so that they have the same number of electrons as the nearest noble gas. Wait, what? There's a lot of stuff there. Well, take a look at sodium. We know that he loses an electron to become N+. Well, if he loses an electron, now he's got the same number of electrons as neon. Okay? That's why he does it, for that strategy. And potassium and lithium, they do the same thing. You only find them as +1. In fact, all the alkali metals are +1 charge out in ionic compounds in the world. All the alkali earth metals are +2 charge out in the world. All right? Same thing for the nonmetals. These guys right here, all the halogens, okay, in 7A, if they gain just 1 electron, they will have the same configuration as the noble gases. So you only find them in the -1 charge, okay? Sulfur, oxygen, selenium, -2 charge. Phosphorus, -3 charge. Nitrogen, same thing, okay? All right, so the main point of all of that was the position on the periodic chart can help you predict what type of ions it'll form in ionic compounds. Alrighty. Predicting ion charges. Okay. We know position on chart tells you the number of protons. Okay? It's the same as the periodic number. Okay. Okay. For atoms, okay, which by definition are neutral, also tells you the number of electrons. Periodic number tells you the number of electrons of any atom. Okay. Now these noble gases. What's a noble color? A noble color, I guess, is blue. Group 8A, okay, elements, the noble gases, are very stable. Okay? That's what I meant by they have sort of the best configuration of electrons. Okay? Oh, actually, that's what I meant to say. Continue the sentence. Very stable electron configuration. Configuration might be a weird word to use at this point in your chemistry career. You know, for the time being, you can certainly think of it as just the number of electrons. It has a perfect number of electrons. Okay. Consequently, okay, noble gases are very stable. All right. Now, big idea here. Let's do that again. When forming ionic compounds, okay, ions form by gaining or losing electrons to have the same number as the nearest noble gas. Okay? All right, so quick example. One right. Oh, here it is. No, this one. Okay. I think I made the point, but what I was trying to say is that, you know, as you go down the periodic chart, you are adding on an electron to those atoms, okay? Helium has one more electron than hydrogen. Lithium has one more electron than helium, okay? And so if you lose one, you have the same number of electrons as the element right behind you, okay? If you gain one, you have the same number of electrons as the element right in front of you. All right, so sodium minus an electron, you get sodium plus, okay? And that is 10 electrons, okay? Just like neon. Okay. Chlorine adds an electron plus E minus and becomes Cl minus and now has 18 electrons. Okay, and that's like argon. Okay. Calcium, in order to be like the nearest noble gas, it certainly isn't going to gain electrons. If calcium, which is way over on the left periodic chart, was going to gain electrons to try to be like the nearest noble gas, it'd have to gain tons of electrons, and you'd start to get just a huge charge. Calcium would be like, I don't know, plus 15 or something like, or minus 15. It had to gain all that amount of electrons. And the more charge, in general, a concept that we're going to see, Mother Nature doesn't love charge. Okay? There are certainly exceptions, or we wouldn't have ionic compounds. But Mother Nature doesn't love charge, and so something that charged is not going to be very stable. So rather than gain all those electrons, simpler for the metals to lose an electron and be like the last nearest noble gas. Okay, so loses 2 electrons, okay, to become calcium 2 plus. Okay, so it also has 18 electrons, okay, like argon. So it has the same configuration of electrons as does Cl minus. Okay. All right. Okay. Oh, actually, yeah, right there. Okay, so concluding idea here. So the periodic chart is very helpful for predicting charges of ions. Okay. This, by the way, is straightforward when you're talking about the main groups, or fairly straightforward. For main group elements, okay, not so straightforward for transition metals. Remember those ones in the middle of the periodic chart. You could almost look at it as look upon it as that they're in the middle, and so there's no real nice strategy to get to the same electron configuration as the nearest noble gas, and indeed they don't, or they don't typically. There are some exceptions to that, but for the most part, they just get closer. Okay. They all tend to lose electrons. They don't tend to gain electrons, but they don't lose enough to make it all the way back to the configuration of the nearest noble gas. Okay. They, like all metals, don't hold on to their electrons terribly well, and so they can be stolen by some non-metal that can successfully get the same number of electrons as a noble gas, but not the transition metals usually. Okay. I'm going to talk a little bit about polyatomic ions. Polyatomic ions, they're a molecule, floating around in the world as a molecule, that for some reason or another could be an acid-base reaction, or it's often an acid-base reaction, but for other reasons, polyatomic molecule, okay, that then becomes charged. And so it's what we call it is a polyatomic ion, okay? And so it's a molecule that becomes charged, and then as charged, it becomes part of an ionic compound. Okay, so getting a little complex there. Okay. All right, so polyatomic ions. Okay. molecule in which the entire thing is charged. Okay. All right, so here's one nitrogen with molecular bonds all around to hydrogens. Okay, if you get that type of arrangement, those are molecular bonds, but the entire thing becomes positively charged. That's actually ammonium. Okay, you've ever heard of ammonium nitrate? It's fertilizer people have used to make explosives. Ammonium nitrate, that's ammonium right there. Okay, nitrate is also a polyatomic ion as it happens. Okay, and then okay, that's sulfate. Okay, you will sometimes see these. We're going to start moving on with them like that. Okay, NH4 plus or SO4 2 minus. Okay. All right. So we've sort of we've learned to appreciate here now that the ions in ionic compounds can have different charges. Sometimes they'll have a +1 charge, -1 charge. Sometimes they'll have +2, -2. Sometimes they'll have -3. Okay. You can have +3 ions. Okay. So, but they're going to come together to form a neutral ionic compound. Okay. And so, if you know what the charge is of the ions, and you know they make a compound, you can predict what the product's going to be. You know, how many of the cations it'll have and how many of the anions it'll have, because the whole thing's got to end up to be neutral. So if it's 1 and 1, if it's a 1 minus anion and a 1 plus cation, you know they got to come together 1 to 1. If it's a 2 plus cation, hooking up with a 1 minus anion, you know that there's got to be 2 of the anion species for every 1 of the cation species. Okay, might seem a little oh boy, it's going to get hard if you. What if you've got a +3 cation and a -2 anion? You'll see that the charges end up being the number of the opposite one. So if you've got a +3 cation, okay, and a -2 anion, you're going to need 3 of the -2 anion, and you're going to need 2 of the +3 cation. If you don't see that with me doing my hand waving thing, then let's put it up on the board and you'll see it. Okay. Ionic compounds and their empirical formulas. Okay. Mother Nature combines ions, so overall compound will be neutral. Okay. Need to be able to predict formula if given the ions. Okay, and it's not terribly hard. Okay, so you have lithium plus and chloride minus, okay? The ionic compound lithium chloride must be one of each, and that's it. But, not surprisingly, they get a little bit more complicated. Okay. Okay. What is the empirical formula for ions below? Okay. What if you have F minus and magnesium 2 plus? Okay, fluoride and magnesium. So that's example 1. Another example, how about beryllium 2 plus, or no, beryllium 2 minus, sorry. Yeah, sorry. Beryllium 2 minus, and iron 3 plus. Okay. All right, so this is a good point. I think you know it because I said it earlier, but why don't you pause the video and do that. You back? Okay. We're going to need 2 of those for every one of those to counteract them. So the empirical formula is usually the cations come first. Okay, so that's going to be Mg for magnesium, F2. Okay. Cations come first again. I don't know why I flipped them like that. So you're going to need, to make the overall charges neutral, you're going to need 3 of those and 2 of those. And note again that it's sort of the numbers of their charge actually becomes the subscript of the other. Okay, so this is going to end up being Fe2 beryllium iron. I don't even know how to say that. 3, Be3. Okay. I liken that a little bit to like, so hopefully everybody sees that. If you have 2 irons, then you've got an overall, why don't I put that up here? Just, you can think of that as an overall 6 plus, okay, because each one is 3 plus. And then if these are each 2 minus and you've got 3 of them, then this is an overall 6 minus, so neutral. Okay, that's why we know those subscripts. Okay. All right. Oh yeah. Sometimes, you know, we see these polyatomic ions. They might be polyatomic ions. Okay. And if you just need one of the polyatomic ions, you only need 1 sulfate. Okay, you just write sulfate. Okay. Occasionally, you'll need more than one of, just like you needed 2 of the irons to make this neutral. Occasionally, you'll need more of one of your polyatomics, and then we're going to do parentheses around it, and then 2. Okay. So I'll show you some examples. So note. How do I say it? If one of the ions is a polyatomic, I don't know if that seems like a big fancy word, but it makes sense. Poly means many, atomic stands for atom, so polyatomic, many atoms. You use parentheses. Oh gosh, I cannot spell parentheses. I think I have that misspelled, but parentheses. If you need more than one of them. only if need more than one. And I'll show an example. Okay, so say that we're trying to come up with a compound for ammonium and bromide. Okay. Or say you're trying to come up with the compound for ammonium. I'll make my plus sign a little bit nicer there. Ammonium and phosphate. It's another polyatomic ion. Okay. All right. Pause the video. You do it. Back. Okay, so we only need one of those and one of those, right? Because it's 1 to 1, so no parentheses needed. Just write ammonium bromide. That's it. It's the empirical formula. Okay. For this guy, we're going to need 3 of the ammoniums to balance out just the phosphate, right? So this guy we'll write the ammonium, and then we'll put parentheses around it. We'll put a 3 right there, and then we'll just write the phosphate. No parentheses needed, because we only need one of that particular polyatomic ion. Okay. All right. We need to learn how to name them, so that's our next section. And you need to be able to go. You need to be able to go from the empirical formula to the name, and from the name to the empirical formula. Okay. All right. We'll get back to that.